Hello, this is Frat Tigrek. In this screencast, I will introduce the binary hypothesis testing. This topic is covered under the third module of the course Statistical Signal Processing. The binary hypothesis testing is based on the likelihood function concept, so it is advisable to check the screencast on likelihood function before proceeding with this module. However, this screencast is meant to stand on its own, so you might as well continue and apply the binary hypothesis testing for detection. Binary hypothesis testing concerns making a decision between two hypotheses regarding the presence or absence of a signal. Let's consider a very simple example to introduce the method. The signal model at hand concerns a DC voltage in additive white Gaussian noise. The additive white Gaussian noise and its probability density function is plotted here, which is also the probability density function of the data when there is no DC voltage present. When there is DC voltage, say 1 volt, then the probability density function for the data is displaced. The expected value for the voltage is now 1 volt instead of 0. So, when we get one data sample, it will be drawn from either one of the distributions, 0 mean with variance sigma squared or 1 volt mean with variance sigma squared. Here's the question. Is the signal, the 1 volt DC, present? The presence of the signal is one hypothesis that we are testing for. The other hypothesis, also called the null hypothesis, says there is no signal, only the noise, hence the name binary hypothesis testing. We want to decide which one of the two hypotheses is valid based on the data we collect. Now, here's the question. What is the criteria to decide which hypothesis holds? The probability density function guides us here. They can be used to determine which hypothesis makes our data more likely, and we can simply choose that hypothesis. In other words, these probability density functions are actually likelihood functions that tell us how likely our data is given a hypothesis. Let's put a threshold at the point where the likelihoods are equal. We have a decision criterion now. If we measure the voltage above the threshold, we decide that there is DC signal of 1 volt. If the measured voltage is below the threshold, we decide that it is just noise. Obviously, we might be mistaken. We can actually calculate the probabilities of detecting the signal and making a mistake. We can write down the probability of detecting the signal correctly along with missing a signal or giving a false detection in a confusion matrix. Now, let's see how these probabilities are calculated. We have two important figures of performance for a binary hypothesis testing, the probability of detection and the probability of false alarm. We calculate these probabilities using the complementary cumulative distribution functions, which are related to the probability density functions by an integral. Basically, we are calculating the area that is under the curve of interest starting from the threshold we choose. Don't forget, we are dealing with probability density functions here. So, when we calculate the area under a probability density function curve for all possible values of our data, we must obtain 1. The cumulative distribution function gives the probability of a random variable having an outcome that is less than or equal to a certain value. The complementary cumulative distribution function is, as the name indicates, the complementary of this cumulative distribution. It is also called the right tail distribution in some textbooks. Now, things get more exciting. We figure out the dependence between the threshold we choose and the probability of detection and false alarm. So, we should be able to choose the threshold to reduce the false alarm probability or increase the probability of detection. But doing so means we are shifting the threshold. Having likelihood under one hypothesis larger than the likelihood under the other hypothesis is not enough. Now we want the likelihood under one hypothesis to be multiple times larger than the likelihood under the other hypothesis. In other words, we are taking the ratios of the likelihood functions and check if that ratio is larger than a coefficient that satisfies our performance specifications. How so? Let's move the threshold and see it for ourselves. Here we have an animated figure that shows how the probability of detection and false alarm changes as the threshold changes. This type of plot, which depicts the relation between the probability of detection and probability of false alarm, is called the receiver operating characteristic. A big name for a modest curve, eh? Well, to modify this curve, you have to modify the hypothesis, such as the variance of the noise or the voltage level of the DC signal in our example. So, this modest curve explains what kind of trade-off you have to make between the probability of detection and probability of false alarm, given the distributions for the hypothesis. Let's see what happens when we modify the hypothesis in the next slide. As the probability density functions are modified by changing their expected values and variances, we can trace the dependence between the probability of detection and false alarm and generate the receiver operating characteristic curve for each case. As you notice, the curves are not very informative when hypotheses are separated further. What is more, there are applications where the probability of false alarm is supposed to be on the order of 10 to minus 6, such as radars. There is no such value visible in this receiver operating characteristic curve. For practical reasons, the receiver operating characteristic curve is plotted in logarithmic scale. With this slide, we conclude the screencast on the binary hypothesis testing. If you have questions about this screencast, please contact us. Have a nice day.